All right, I want to thank the organizers again for the opportunity and then share some of the recent experience that I had with brilliant former postdoc and former students who's now a postdoc here at UCLA. This is actually the work started like maybe 4 years ago before those guys left Georgia Tech and then dragged on for a while, and then I hope that I can share some perspective. And I probably will use a method that Professor Alsher mentioned that is not recommended, the characteristic strategy to solve Hamilton Jacobi equation. But I'll try to be a little bit on the explanation side that sometimes it is useful. And hopefully I can give you an explanation why we view it as useful. Here's a brief outline what I'm going to talk about. I'll start with motivations, why we want to do it, and then the algorithm, the bound of the residual, which will try to give some mathematical justification. This is actually give you some meaningful computations, and then show some of the examples. Oh, sorry, I'm pressing the wrong button. I hope it is disappeared. All right, let me get to the these objectives for the project that we want to do. And obviously, it's try to solve Hamilton Jacobi equation, which I don't need to explain. And the other motivation is try to use it in the control context, and which very easily you have to deal with higher dimensional situation. But I'm not going to touch any of those application background, just purely a Hamilton Jacobi equation with a given initial condition. That's the problem setup. And of course, I'm considering this problem in a higher dimension, meaning that higher than the normal one, like a 4 or 5 dimension, or even up to 50, 30, this kind of dimension. One of the challenge, like I don't need to explain to this audience, is that the curse of dimensionality. And every time I mention curse of dimensionality, it is always a strange feeling. I can share slightly later why I have a strange feeling. But also, I would like to use this strategy to say there are also mathematical opportunities you can actually show your computation is meaningful, not just, oh, it looks good, but also mathematically meaningful. And you can also use this kind of formulation to show maybe there's opportunities to even say something theoretically about the original equation beyond the singularity situation, which is a challenging mathematical problem on its own. And to the end, I may have more questions than you have, and I hope that you don't mind that I share those questions, because I don't know how to answer some of them. All right, let me actually say a few things about this high computational course, the curse of dimensionality. And this is actually connected to many of the previous talks, like a Professor Alsher's talk, a Professor Liao's talk, my colleague, giving this intrinsic low dimension, high dimension ambient space. But if you really think about approximate a function in a higher dimensional space, what do you really want to achieve? You actually want to achieve that the accuracy almost everywhere. And now, if that's the situation, you would ask yourself, is that possible I can actually approximate the function without sampling at that location? I mean that when I say these things is that if you in a higher dimension, you sample, it becomes very sparse, and then there are big holes in the region. And if I have a big hole in the region, I don't have any sample, can I actually say I'm good in that region? And of course, you can actually say sometimes it is good in that region. And if your function is in a lower dimensional submanifold, and you captured that from the neighboring or the far neighboring information, right? That is one situation. Or the function is, the structure is so simple, you can capture it very efficiently. Those are probably the situation most of they actually make me feel a little bit controversial of talking about curse of dimensionality. And that's the reason I was always hesitating saying that, oh, we actually solved the curse of dimensionality in that way. Because really, your function can be sampled efficiently in high dimensional space is really because it has a low dimensional structure and you find a good way to capture it. That is what I interpret. But on the other side, there are a lot of questions that you really need higher dimensional situation, which they are actually complicated in higher dimensional space. And then what are you going to do with that situation? Are you going to sample everywhere in the way that you would capture everything? Then the question is that if you do so, then curse of dimensionality comes back. Because it's just like filling points in the volume, right? So that is the reason why I'm always a little bit hesitant of thinking this question. And I actually borrow a quote, say, from a talk that I listened to 2 weeks ago by Professor Jinchao Xu. Says and he put this simple saying that if you use only a few points to sample a high dimensional space, and you say that you're good, and there are only two situations. One is there's no error guarantee for you, or your function is super simple. That's pretty much the situation. But so in this situation, how do you actually still addressing the issue? I want to compute high dimension, but I don't have the ability to sample a lot of points. And that's the place where I want to actually get into it, see where you can actually do in a reasonable fashion. That's why the title, supervised learning with coupled strategy, which I'm going to explain. And of course, talk about using neural network to solve PDEs. There are a lot of work that I could actually just run the entire talk by reading the names for the entire morning, and probably won't be able to run, will run out of time for doing that. So that I will just take a few commonly known ones, like say the deep race, the PNN or WAN, this type of a general strategy to solve PDEs. You could apply them to higher dimensions. And they are not specially designed for a particular PDE, and it's kind of a strategy you can use for any PDE. And but if you focus on Hamilton Jacobi equation, then there are a lot of work in recent years. I think that the UCLA is a dominating place in that regard, probably by Professor Alsher for that reason, because we all get influenced because you like Hamilton Jacobi equation. So everybody graduated from here has to like Hamilton Jacobi equation. Otherwise, we will not get our diploma. Or I failed my defense. All right, I'm not going to go over this one because you probably know him better than me. And I want to actually mention something. The strategy I'm going to actually share with you is more related to this Hamiltonian process on Wasserstein manifold. And this is a concept that kind of like not so commonly known, not like the gradient flow structure, which is much broadly discussed. And the Hamiltonian system, I have to mention my former colleague, now the Professor Wilfred Gamble, used to be at Georgia Tech, which I benefit a lot talking to him on various of Wasserstein manifold problems. And it inspired me to study many of the subjects that I want to do. So this is you use Hamiltonian techniques on the probability manifold to solve problems in related way. And that's where I'm going to head to. So let me actually use the example, probably duplicated a little bit with Professor Alsher's talk, and to explain the intrinsic idea behind where we try to head to. And then I will try to generalize to broader situation. Let's just say you have the Hamilton Jacobi equation, the simplest one of them. Your Hamiltonian is just square, p square. And then you give in initial condition. And this is probably very familiar to many of you, especially the students here. Probably you have to take courses on how to solve them numerically. At least when I was a student, this is one of the probably homework. You have to actually do it. And then one way that I can actually look at this system is by coupling it with a continuity equation. So this equation, it's the standard continuity equation. You take these two together, that's a well-known equation. It's the Wasserstein geodesic equation, except I have one difference is that Wasserstein geodesic, you give an initial density, a target density, and then you get the closest curve. But I actually don't have the target density. Instead, I have an initial value and providing the velocity field if you take the gradient of g. So that is slightly different, but it is still the same equation. Now, this one you can actually look at it from a different angle, saying that, oh, I just take everything on the probability manifold, and I take this rho, and this is the gradient you provide me, the vector field, the transport to different places on rho, the manifold spanned by rho. Then you can actually view this whole thing, these two equations, right in this fashion. And this probably remind many of us learning undergraduate dynamic system. This is a way of writing dynamic system, but you're deviating a little bit from the regular Euclidean space. You go to the Wasserstein manifold to do this type of things. Well, of course, this has perfect explanation in the classical mechanics, is that, well, you can actually think this as a particle motion in the standard way, saying, I sample according to the initial density, a point, and then move forward according to a Hamiltonian system, which is the characteristic, the bicharacteristic, because I lift up in the phase plane, right? Then this is probably a similar formula as Professor Auscher's one, except that we fall short, like kind of didn't get to the completely U formulation, but this is something. You can write the solution in the characteristic. Characteristics are straight lines in this situation. You plug in here, you will get the formula in that way. But you can also look at this from a slightly different angle, which is also similar to Professor Auscher's approach, is that if I look at from an optimization point of view, I'm actually trying to match a function, taking the gradient, evaluate at the x point to the p point. If I look at it from that angle, this is actually a way saying that if you can find a function that become the minimizer of these things, more likely you will get the solution of the Hamilton Jacobi equation. That is one of the strategies that we're going to use, saying that, well, let's minimize these things. You replace this by neural network and minimize it. Right? This is a simple explanation. I hope illustrated the roadmap in some way. And if I summarize, this is what we're going to do for the entire thing. Is that you couple Hamilton Jacobi equation with a continuity equation to form this so-called Wasserstein Hamiltonian flow. And then you formulate a regression. You can use Bregman divergence or you use least square. It doesn't really matter. In certain level, they actually are equivalent. You can prove it. And the minimizer satisfies this Wasserstein Hamiltonian flow. Of course, Wasserstein Hamiltonian flow, I will explain in more detail that there's a particle version to it. This is you can generalize this not to just the straight line characteristic. You can generalize into many other characteristics. So you have the particle dynamics, and you use this particle dynamics to generate data to train your model. So this is not an arbitrarily sample situation in the most of the existing strategy. Rather, I have coupled P and X sampled in a particular way by my ODE, characteristic ODE, and I do it in that fashion. So that is the roadmap. Let me try to explain each step on the way. This is like you have the Hamilton Jacobi equation, you multiply rho, and then you do the continuity equation coupling. This will give you, of course, everything is understood in the weak sense, and you have to do the integral and test function integration by part that I'm writing in this fashion just for convenience. And you have this coupled system. This will be a Wasserstein Hamiltonian flow using that one. And I can always write its corresponding Hamiltonian system in this fashion. And this is a slightly different than most of the random perturbation version of Hamiltonian system. I'm actually assuming my initial point are random. And the vector field is not really random. It is the given initial condition that you provide. The G is a deterministic function. And I take the grading of this function, evaluate at the sample points. That's my initial velocity for the characteristic. So somehow this is actually a little bit strange setup compared to most of the way people introduce randomness for Hamiltonian system. Normally people do Hamiltonian system, there are two typical ways. One is both initial conditions are random, or you have both equation added Brownian motions. And this is not that way. This is actually halfway. It's in the middle. Like say I have one is random, the other one is not. Then I will have this generated data. Once I have the data, then I'll form this either a least square version of it or the more general divergence version of it. This is just simply saying that the distance between this function and that function has to be close after you do the minimization. That is pretty much the central idea. And of course, you can replace this by any other ways. And the two things we tried in our numerical experiment is the least square and the Bregman divergence. Then you use this as the loss function to train your neural network. And I think that part is pretty easy. I mean, we use Atom and we use ResNet, all this kind of routine type of things. Did not do anything particular. And I don't think the neural network is big. It's relatively small. That is the thing. Now, if you find the minimizer of this function, what can you say about to the original Hamilton Jacobi equation? And because you're not really solving the Hamilton Jacobi equation. I mean, at least we did not solve directly. We solve a minimization problem. And it's connected to the original Hamilton Jacobi equation in the following way. You take the grading of what you found as minimizer, and it goes to 0. So it is kind of like a spatial constant function, could change in time, and that's the differences. And then you try to find a way to determine that time-dependent function if needed. So that is, this can be true for either loss function that we mentioned earlier, but I believe if you change to a different reasonable function, you can still prove this kind of result. Well, like the connection, maybe I skip this part because it's kind of become boring. It's like kind of showing how do you actually really show this is correct. Let me skip it. Let me actually just highlight a little bit properties about this scheme. The computation of the PDE is converted in ODE simulation. And you need a lot of particles, which is probably sometimes become unpleasant. It depends on how many particles you use. And of course, that depends on the dimension and depends on the application that you need. But at least, because it's ODE simulation, even if you have maybe 10,000 particles, each one is 20 dimension, you can still compute it in the regular computer. It's not something you cannot compute. So that's the reason why I say at least it is allow you to scale up in dimension. because the real computation is really done in the ODE level. And then you do the training. Of course, training is just whatever the data I generated, I'll use those things to train my data. And of course, there's something like tricky, I've not touched it, is that how do you actually really select this initial density, which is a tricky thing. And of course, it's important. I don't really have a good recommendation, except that arbitrarily take as Gaussian at the location where I'm interested in. I thought like maybe in applications, there are probably a lot of different ways you can actually pick your favorite ones. That is something probably need to be studied more carefully. In the ODE solver, you can actually use more geometric integrator, like can preserve a lot of quantities, so that when you do the learning part, those quantities can be preserved as well. This is we can actually show some of the properties on the ODE level, but once you do the learning, I have no idea whether they will be preserved or not. And hopefully, the principle of supervised learning, it gives some benefit of doing it. One of the other advantage I see these things is that in the optimization formulation or the data generation step, you never actually see anything, the characteristic intersection. You may have the X intersection, but the P is different. So the uniqueness of the ODE guarantees you can actually move forward beyond the characteristic meeting in the standard situation. So this setup in some way does not see the singularity formation in some way directly, but it is, you have to actually understand from a different perspective, which I try to explain slightly later. Yeah. But of course, you can actually say that how is it, if I actually find the minimizer in some way, I don't know how this is guaranteed by optimization algorithm, because that's another challenging part. But assume that I actually get that minimizer, and what can I say about the minimizer to the original equation? And here is a theorem. I don't expect you to read everything. I try to explain. This is actually, if you look at this side, it is essentially the residual of the equation understood in a way that is a grading version of it. That's what I actually started with, like saying the difference between the Hamilton Jacobi equation I'm talking about to the original one differed by a grading version of it. But of course, you can integration by part move that integral to the test function if you really want to dig it out. But it can be controlled by various of variables that you used in this process. For example, number of samples, that's capital N. The step size when you solve the ODEs. I mean, we use for the Euler, not necessary for the Euler, like a symplectic version of Euler strategies. You could use other ones, and I don't think that make a huge differences in this analysis. And then those are small parameters. I mean, those are constant. Those lambda, mu, and r are constant. And those delta and epsilon are small numbers that is actually depending on the neural network that you pick. And it is not saying every neural network will do the good job as well. Of course, good neural network will make that smaller. Not so good neural network will make it bigger. So that is a quantity that is associated with. And if, in fact, that you can analyze, it is essentially determined by the tangent plane of your neural network. But anyway, so that is, you pretty much can see the routine estimate from this kind of understanding. Let me actually say quickly about the weak solution that what I actually refer to. This is actually a formulation from that objective function in the minimization, you can actually say if you find a minimizer, it actually satisfies the Hamilton Jacobi equation in the following sense. This is not the typical way that you understand the weak solution or the viscosity solution. And I think like Zhou has who's in the audience has a very interesting understanding, and he wrote a note that we didn't include in the paper, but explaining how this formulation is actually related to the viscosity solution. Is that if you, this is the key is at this conditional distribution. If you have x and then there are multiple p in that x position, and what is this conditional density? If you take this conditional density happen to be a minimizer among all the p's at the same x, that gives you back the viscosity solution. So it's a degenerate situation, you get back the viscosity solution. But whether this is actually another version of weak solution, I have no idea, but I would say that at least if you understand it in this way, you don't really need to worry about the singularities. Because everything is integral form, it is defined by data that doesn't see any of those intersections. A particular situation is that if you actually take this special form, P is squared, and then this is the potential, then you would actually, this thing can be put as a simple form. Let's say that you match the vector field with the momentum you computed from ODEs. It's very simple, and then weighted in this way. This is actually the whole point, is that if you go back to my theory, I have this weighted. This is the empirical weight that the data generated the weight. It's saying that if I have samples, it will be good. If I don't have samples, it's bad. That's pretty much the message that I want to say. It's that I'm only guarantee my solution, the residual of the computation is good when the sample points, where the sample points are concentrated. But if outside these sample points, you don't really have any knowledge, which is okay because you didn't sample anything. Why you expect you get something there, right? So this is actually one of the message that I want to say, that in the high dimensional situation where you don't have the ability to sample everywhere, then sample smartly following the characteristic and only claim that we can actually get a good result in that region that we sampled. But of course, you have to sample in the cohesive way, meaning that your P and X has to be coordinated. If you sample it just randomly saying that, or P sample few points, X sample few points, you don't get what you want. So that is one of the messages, saying that you can actually sample in a smart fashion that allow you to claim your residual is small within this weight. All right, so that is, let me show a few examples to illustrate. I think this is a 2D example because we have exact solution. And so we can really go and evaluate what is the error, what is the residual, and the black dots are the places where we get the sample. Of course, the sample is actually generated at different time. This is, I think this is a different time. And the samples are generated by the ODEs. And they actually go according to the dynamics. Initially, I believe it's Gaussian. And then you get to regions, and then they will focus on a place, and then they will actually move to the other side, and so on and so forth. You can see it. And the top part is the residual. It's the quantity that the theorem says, like it should be small if my sample place is. The white is the small place, and the dark region is that the residual is big, which is exactly what we actually anticipate. And the error, if you look at the bottom part, because this situation, we actually know the exact solution. So the bottom part, again, the white part is the small error part, and the blue part is the bigger error part. And we can only say that the error is small in the regions where we sample it. But besides that, the neural network is whatever the coefficient it defines, and they will have the solution in there defined, but it is not meaningful at all because you never trained anything there. Right? So that is just a verification to see how this is corresponding to the theory that we have. This is the same kind of setup, but we just put it in 20 dimensions. And of course, then the sample points becomes very sparse in this situation. You can actually, I mean, it's still same setup, but you plotted, I believe, is 5th and 15th. I think this is Zhou's favorite slice. It's just like a 20 dimensions, 5 and 15. All the plots in that way. You probably find a similar thing is 5, 15 in the papers you wrote together. But anyway, so those are the sample points locations. You can actually see the red ones is the exact solution. The blue ones are the computed solution. And you can actually see that at the concentration of the sample points, they agreed quite well. But move away from there, there's no agreement in that sense. And you look at the vector field, and you look at the vector field, they matched pretty well similarly. This vector field is generated by the neural network solution. I learn the function solution, and I take the gradient, and that's the plot that I have here, versus the original ODE, the P that I have. But anyway, so this seems to be agree in a certain way. This is actually another situation, I think it is in 20 dimension, but it's a very different Hamiltonian, and the initial condition is a cosine function. This is again another situation you can actually get the analytical solution to see how well the performance is. This is a slice, I mean, taking a diagonal line and look at the solution, whether they agree on that line. And you probably see that the derivative part, which is because our solution is agreed on the derivative, enforced on the derivative level, and this is the solution itself. If you take the solution itself, you can see that, I mean, it's very difficult to see it, but hopefully you can recognize there are two curves, but pretty close. This is along the diagonal line, and I plotted out, because otherwise it's very difficult to visualize. This is one of the challenge that in higher dimensional computations, don't know really what is the best way to show the examples. This is a situation where you have a 30-dimensional sinusoidal potential, which is kind of complicated. And you can actually see that the computation, this is initially it is two Gaussians, and you can see the computation and forming, and you do see the singularities coming out of these things if you project it down. But if you look at the solution itself, it is folded in a strange way. But you can actually compute it. We don't know the true solution, so. But we guess that there's a singularity about 0.4 in this region. You probably recognize that too. And we just guess, but we don't know whether this is the situation. This is a non-separable Hamiltonian, which is like you have the Hamiltonian is written in this strange way. And this is a 10-dimensional situation. You can actually see it goes above and then coming down. And at some point, there's a flip happening, and there's a singularity in that process. And why I say there's a singularity is 0.65. And here is the plot to illustrate why we actually think there's a singularity, is the following thing. If you look at the error, I mean, this is residual, we call it, it's the loss function that we minimize. If you look at the loss function, it maintained pretty small all the way until like you get close to 0.4, and then start increasing and then decreasing again. And this is the reason why we think that at the peak time there must be a singularity, because the theory that I presented have a lot of assumptions I didn't read, and those assumptions have regularity requirement on the solution. If you have singularity, you don't have those things, so the theory fails in that way. But after passing the singularity, the solution seems to come back in that sense, which is kind of strange. All right, so that is pretty much all the examples that I want to illustrate. I don't know how many minutes I have. 5 minutes? Okay, all right, I'll just entertain you with one of the equation, and I showed Professor Stan Osher yesterday. You can actually use this kind of things to not using the coupling, but you can actually use the Wasserstein Hamiltonian flow to study many of other PDEs. For example, the Schrödinger equation, nonlinear Schrödinger equation. And this is a classical way of writing. You do the transform, the Madelung transform, and you convert it into this phase and amplitude equations. It becomes a Wasserstein Hamiltonian flow. And if you take that viewpoint and you use push forward ideas, then you can actually write an equivalent formulation that the Schrödinger equation mathematically equivalent to this original one in this form. This T is the dynamic. It's the push forward operator. I'm actually describing the push forward operator, how it moves in time. And it looks kind of a little bit strange, but probably make a lot of sense if you look at the second order differential equation, the original particle version of Schrödinger equation in this second order version. This has a lot of similarities in that way. And you can further kind of parameterize this push forward map by neural network or by whatever the favorites of discretization strategies. You can actually solve Schrödinger equation in this way. And we have a lot of examples to show that. But I don't want actually bore you with a lot of mathematical discussions. But let me actually just summarize here. I hope that I kind of use this simple example to show the coupling strategy can help you to avoid kind of like a sampling in the entire space in some situation. And you can actually prove certain mathematical bounds, and you can actually argue this can define different weak solution in a different sense. But really that there are more questions than you could ask. For example, how this weak solution, if it is really a weak solution, I believe so, but we never proved anything except a few like understandings in certain way that is meaningful. But how does this connect to the general weak solution in the classical situation? How do you actually go define it beyond the singularity? Those becomes a very interesting analytical question, but also you think about the selection of initial density. This becomes sometimes tricky. I mean, most natural thing, you do the initial Gaussian or initial mixture of Gaussian or even like a uniform sampling, the common ones. But what about if someone say, oh, I want to know the solution at a certain time, at a certain place? That becomes a little bit trickier because you don't really know which group of particles will evolve to that place. And if you actually have that situation, this really becomes a problem of two-point boundary value problem. I think this is very much related to the mean field game and many other things that people are interested in. Yeah. All right, with that, I want to stop here and thank you for listening.